The locomotive shouldn't have been moving. It had derailed 90 minutes earlier, tumbling down an embankment in a tangle of twisted steel and shattered wood. The frame was bent. The boiler was damaged. 2 driving wheels were cracked. Any reasonable assessment said the machine was finished, destined for a scrapyard, or at best, months of shop repair. Instead, at 3:47 p.m. on November 8, 1917, that same locomotive fired its boiler, coupled to its own wreckage, and began pulling the remains of its train 200 miles back to the railroad's main shops. What should have been an engineering impossibility became a testament to how tough steam locomotives actually were when survival mattered more than specifications. The Great Northern Railway operated freight service through Montana's rugged terrain, where grades were steep, curves were sharp, and derailments happened often enough that crews knew standard recovery procedures. On November 8, 1917, as a westbound freight pulled by Locomotive 1372, a 280 Consolidation type built in 1903, was climbing a modest grade near Cutbank, Montana, when something failed in the track structure. Later investigation determined a rotted timber support under the rails gave way under the locomotive's weight. The front truck derailed first, pulling the entire locomotive off the tracks. The tender followed, then several freight cars. The whole assembly tumbled 20 feet down an embankment, as coming to rest in a chaotic pile of metal and broken wood. The engineer and fireman jumped clear before the locomotive went over. Both survived with minor injuries. The brakeman in the caboose felt the emergency braking but stayed with the train as it derailed. He also survived. By the standards of 1917 railroad accidents, this was relatively minor, equipment damage, but no fatalities. The crew walked to the nearest telegraph station and reported the derailment. And the railroad's standard response would involve dispatching a wrecker crane, clearing the debris, and hauling the damaged locomotive to shops on a flat car. That's what procedures specified. That's not what happened. The wrecker crane was 200 miles away, dealing with another derailment. Montana in November meant weather could close routes quickly, and the railroad couldn't afford to leave valuable equipment sitting exposed to the elements while waiting days or weeks for recovery. The dispatcher sent a message to the crew. Assess whether the locomotive could move under its own power. If it could, bring it home. If it couldn't, secure it, and wait for the crane whenever it became available. The engineer, whose name appears in railroad records only as Henderson, climbed down to examine Locomotive 1372. The visual damage was extensive. The frame was visibly bent, twisted by impact, and the weight of equipment that had tumbled on top of it. And the boiler had dents and what appeared to be stress cracks near riveted seams. 2 of the 8 driving wheels had visible fracture lines. The pilot was completely destroyed. The cab was damaged but structurally intact. The tender had separated from the locomotive, but appeared mostly undamaged beyond bent coupling hardware. Henderson made an engineering judgment that the railroad either respected or was desperate enough to accept. The locomotive might be able to move slowly if the boiler held pressure and the damaged wheels didn't fail completely. The risk was that catastrophic failure during the journey could cause worse damage or potentially injure whoever was operating it. But the alternative was leaving expensive equipment exposed to weather and potential theft while hoping a wrecker became available before winter set in. The crew spent 4 hours clearing debris and preparing for an attempt. They used track jacks and timber to lift the locomotive enough to slide damaged wheels back onto rails they laid in the dirt beside the embankment. They manually reconnected the tender, using chains where normal coupling hardware had bent beyond function, and they inspected the boiler carefully, looking for damage that would make pressurization dangerous. Dents and stress cracks were concerning, but not necessarily fatal if pressure was kept low and movement was slow. At 3:47 p.m., the fireman lit a fire in the firebox using wood scrounged from broken freight car contents. Building steam pressure in a damaged boiler was dangerous. If weakened seams failed under pressure, the boiler could explode, killing anyone nearby. Henderson monitored pressure carefully and keeping it well below normal operating levels. After 90 minutes, there was enough steam to attempt movement. The locomotive moved, slowly. The damaged frame created friction and unusual stresses on mechanical components. The cracked wheels held together but transmitted vibrations through the entire machine with each rotation. The bent frame meant the locomotive didn't track straight. It pulled slightly to one side, requiring constant attention from the engineer to keep it approximately aligned with the tracks. Behind the locomotive and tender, the crew coupled what remained of the freight cars. Most were damaged beyond immediate repair, but several cars had stayed upright during the derailment and contained cargo the railroad didn't want to abandon. The decision to pull damaged cars added weight and risk, but made economic sense. If the locomotive failed during the journey, at least they'd have moved valuable cargo partway to recovery points. If the journey that should have taken 12 hours at normal speed stretched to 43 hours. The locomotive couldn't sustain speeds above 15 miles per hour without excessive vibration from the damaged wheels. Several times during the trip, Henderson stopped to let the damaged components cool, worried that continuous friction and stress would cause complete failure. Railroad dispatchers cleared the main line, routing other traffic around the slow-moving wreck train, and the damaged boiler required constant monitoring. Steam pressure fluctuated as stress cracks affected circulation. The firemen worked continuously, adjusting fire intensity to maintain enough pressure for movement without risking pressure levels that might cause failure. Water consumption was higher than normal because the damaged boiler leaked steadily through compromised seals and stressed rivets. At helper stations along the route, crews provided assistance, and they added water to the tender from trackside tanks. They provided additional coal since the damaged locomotive was burning fuel inefficiently. They offered to halt the journey and wait for crane recovery, but Henderson insisted the locomotive could complete the trip. The mechanical damage wasn't getting worse during movement, and weather forecasts predicted heavy snow within days. Better to keep moving while conditions allowed. At the most dangerous moment came 70 miles from the destination shops. One of the cracked driving wheels developed a piece that separated partially. Not a complete failure, but enough that metal fragments could jam between wheel and rail, potentially causing another derailment. Henderson stopped, and the crew spent 3 hours using sledgehammers and cold chisels to remove the loose metal piece, creating a driving wheel with an irregular surface, but no loose fragments. The repair was crude, but effective enough to continue. Locomotive 1372 arrived at the railroad's main shops in Whitefish, Montana on November 10th, 43 hours after beginning its damaged journey. It had traveled 197 miles, close enough to the estimated 200 that railroad workers rounded up in later retellings. A shop foreman examined it and confirmed what the journey had demonstrated. The locomotive was severely damaged, but had remained mechanically sound enough to move under its own power while pulling its own wreckage. The repair process took 6 weeks. The frame was straightened using hydraulic presses and heat treatment. The boiler was removed, stripped down, re-riveted in areas where stress cracks had propagated, and hydrostatically tested to confirm it could hold normal operating pressure. The 2 cracked driving wheels were replaced with new castings. The pilot was rebuilt. The cab was repaired. Damaged components throughout the running gear were replaced or refurbished. By January 1918, Locomotive 1372 returned to service. Railroad maintenance records show it operating for another 24 years before being retired in 1942 and scrapped as part of the wartime metal recycling effort. And the locomotive that had pulled its own wreckage 200 miles went on to have a longer service life than many locomotives that never experienced severe accidents. The incident became part of railroad worker folklore. The story got embellished in retellings. Some versions had the locomotive traveling 300 miles. Others claimed it pulled twice as much wreckage. The basic facts remained impressive enough without exaggeration. A severely damaged steam locomotive, operated by a crew willing to take calculated risks, completed a journey that engineering specifications said shouldn't have been possible. The incident also demonstrated the fundamental robustness of steam locomotive design. These were machines built with massive tolerances and redundant strength. Frames were over-engineered because designers expected abuse. Boilers were built with safety margins far exceeding normal operating pressures because boiler explosions killed people. Wheels and running gear were designed to handle forces many times greater than standard operation generated. This over-engineering meant that when components were damaged, the machine often retained enough structural integrity to continue functioning, albeit at reduced capacity. Modern railroad operations wouldn't permit what Henderson attempted. Regulations require detailed safety inspections before moving damaged equipment. Insurance liability concerns prevent operating machinery with visible structural damage. But the economic calculation has changed. Modern locomotives are expensive enough that risking additional damage to save recovery costs makes poor financial sense. Crane services are more readily available. The calculus that made Henderson's decision rational in 1917 Montana doesn't apply in contemporary railroading. What remains relevant is the engineering lesson. Machines built with massive strength margins can survive damage that exceeds their nominal specifications. The locomotive wasn't designed to operate with a bent frame, a damaged boiler, and cracked wheels. But the designers had built so much extra strength into each component that even with multiple systems compromised, enough structural integrity remained for limited function. The machine degraded gracefully rather than failing catastrophically. Locomotive 1372 pulled its own wreckage 200 miles, not because of any miraculous engineering, but because steam locomotives were fundamentally overbuilt machines that could tolerate abuse their designers never explicitly planned for. But Henderson's willingness to attempt the journey demonstrated either impressive confidence in steam locomotive robustness or a practical understanding that waiting for crane recovery in Montana winter weather posed its own risks. Either way, the outcome validated his judgment.